because assignment 3 and midterm already test you extensively on that. So yeah, so some parts of a ER diagram, some parts of mainly on the functional dependencies and normal forms, and some parts on the relational algebra. Okay, so the website is also already open. So we can double check the answer over here. Let me see. I can actually open it with PDF. Because PDF I can select and nope. I'm pretty sure last time you can actually write on PDF. Let me see if I can draw here. Definitely cannot. Okay, so we'll just use Notepad to do our working. Can you all see the question? Right, so again for this one is actually pretty. For question 1 it's actually quite simple because what it asks is whether things are in the F plus. Yeah, and as you know, F plus is basically everything that is implied by this set of functional dependencies. So the way here is to look at everything that is trivial and it must be there. Okay, so basically for question 1, everything that is trivial will be automatically there. This includes A, B is not trivial, C is not trivial, D is not trivial. Okay, and then for every one of this, so let's say you consider B, what you have to do is simply compute B plus. Okay, this is option A is because it's trivial, so it must be there. For option B, the left hand side is B, so all you have to do is compute B plus with respect to F. So B plus, you can get AC, so you can get A, B, C. Right, so from A you can get D, so you can get D again here. You can get F, and the only thing you cannot get is E. Okay, but this is enough because our right hand side is only BC. So BC is inside there, so it must be implied. Okay, and then for C again, the same thing, compute C plus, you get A, B, C from here. Okay, and then A, you can get D again, and then you can get F again. Right? So here we have DE. E is not here. E is nowhere in the right hand side. So this only has D. So this one is not. So again, for option D, you can also see that D plus will not have E. Will not have E. Okay, because E is nowhere on the right hand side. Okay, so this one again is not. Okay, which means that E is automatically out. Okay, so again you do exactly the same thing from here, but now it's only for the trivial ones. The notion of triviality is that it must be reflexive. Okay, so let me give you all the 3 Armstrong axioms. The Armstrong axiom states that 1 is reflexive, and in our reflexivity, here we have A to B, and our condition is that B must be the subset of A. Okay, so many of you got this wrong in assignment 4, where you say that A to ABC is reflexive. Okay, so this is not correct. Yes. So you have A to B. Augmentation. You can augment with A. You can get this, right? But by the definition, this is a set. Set does not have any duplicates. Yes. Okay. So that's reflexivity. So augmentation is that augmentation. You basically add. You have A to B. You then add C on both sides. Like this. So you get AC to BC. Now, remember the notation C. So A, B here, anything that is lowercase is a set of attributes. C is also a set of attributes. You can actually add as many attributes as you want. Which means that if you have this, you can augment it with any number. So you can get A, C, D, E to B, C, D, E. Because the augmentation is with B, C, D. In fact, you can then augment with A, B, C, D to get A, B, C, D, E. Okay? So you should try to read the definition very, very closely. This one is a set of attributes. And this is the trick that you can use on assignment 4. Because if you don't augment with multiple things, you can never do it in 5 steps. Okay, so there's augmentation. Besides augmentation, there is the reflexivity. So reflexivity, you have A to B and B to C, then you will get A to C. Okay. Here I was quite pedantic in this sense, is that when you say reflexivity, you need to give 2, right? So no, it's not. Sorry, this is transitivity. When you say transitivity, you must specify two of the functional dependencies that you want to join. What you need is that the range of one is the domain of the other. Okay? You need to make sure that this one is exactly what this one is. Otherwise, transitivity will not work. Okay, something a little bit about the Armstrong axiom is the reflexivity. If you have studied about relations, basically what you have is that for any relations R, so this is a mathematical relations. A mathematical relations is basically you have R, kind of like your predicates. Rxy means that x and y is related, and the relation is through the use of R. Okay, so you can think of relations as if they are predicates, where they return either true or false. It can encode any kind of functions. Okay, so for any function f that returns y, okay, so function takes an argument and then returns something else, another value. So given any of this, you can say that they are in the relations called the image. The image of x is fx. Okay? And then we know that fx is actually y. So you can then transform every function into a relation. And typically, in a mathematical sense, we treat them as kind of equal. Function, so function is a mapping. So function is a mapping between value to value. Whereas relation is a mapping between value to Boolean. You can have a relation with a single argument. If you have a relation with a single argument, for instance, our x like this is what we call as a set. You are asking whether X is in the set of R. Okay, so that's the mathematical part of it. Now, in most of the relations R, we say that the relations is reflexive if and only if for all X we have R X X. Okay, notice this is a very strict condition. The two must be exactly the same. Now, if you transpose this to the Armstrong axiom, it means that it can only admit this. Okay, you can never admit A to B where B is a subset of A. Okay, so the notion of relations in a pure mathematical sense does not apply on the Armstrong axiom. This is a stronger form of reflexivity. Because if you only have this form of reflexivity, you can never actually derive this stronger form of reflexivity. Right? So if you only have this together with augmentation and transitivity, you can never derive this. So the Armstrong axiom has a stronger form of reflexivity, and that is because this is derived from the notion of a hypergraph. In the notion of a hypergraph, you have a hyperedge where the connection is not between one node to another one node. So an edge connects a single node to another single node. In a hyperedge, what you have is a set of nodes to another set of nodes. Okay, so it connects a lot of things together. So let me show you with paint. Okay, so typically the way we draw it is something like this. You have A here, you have B. We merge them together. And then let's say it goes to C, D, and E. Okay, so this is a this part is what we call a hyperedge. So again, a single hyperedge can now encode an entire set or entire subset. In fact, okay, so that is only for non-directed hyperedge. Non-directed hyperedge basically gives you a set. A directed hyperedge can now give you a direction, and this is something more than just a set. The typical meaning of this is basically if you have these resources, the hyperedge is a production rule that you can produce this. So given AB, you can produce CDE. Now obviously, given A and B, you can always produce itself again. Well, it means you have a leftover of A and B. You assume infinite supply of A and B, right? Which means that from any parts of this, you can always discard any one of them, and then you can just produce partially. This is a partial production. You can produce A and B again, and that is why you have the reflexivity axiom of the Armstrong axiom as being B is a subset of A. Okay, now reflexivity basically encodes everything that is trivial. So as long as you can apply reflexivity rule, reflexivity axiom, that means it is trivial. In this case, only A is trivial. Alright, so any questions on this? Now, for question 3, this is non-trivial. But not only that it's non-trivial, it must be not completely non-trivial. As we know that this one is non-trivial. And as we know that this A and B are the only two that is implied. Okay, so we need to look at B only. And in B, this is non-trivial, and in fact, it is not completely non-trivial because you have B to B. Okay, now for question 4, is the same, but this is all completely non-trivial, and then basically the answer is nothing. None of the above, because this one is non-trivial, but it's not completely non-trivial. Okay? So we can actually now test this. This is basically checking whether it's trivial or non-trivial. So if you check A to A, the relation is A. Check whether it's trivial. It is trivial. Okay. Now you can also check a lot of things. These are the parts that are trivial. This is the part that are non-trivial. And there's nothing that is completely non-trivial. You can also non-trivialize it to get this. This is the functional dependencies that is implied in F plus, and this is completely non-trivial. Okay, so any questions on this? Okay, so the first part is basically just giveaway questions. Question 5. Now you look at minimal cover, and this one was rather evil in the sense that you need to compute all. You need to compute all possible minimal cover, and then as long as any one of these is inside some of those, then you're done. Okay. The easy way to check is that, well, look at this. This is trivial. Anything that is trivial is redundant. Okay? So you can never require to have this. So A is definitely out. B to C here. You can then start by first deriving one possible minimal cover. Okay, so let's try to derive one possible minimal cover. From there, hopefully we can figure out everything that is possible to discover over here. Now, we need to look at everything that is have multiple right-hand side, multiple left-hand side. Those that have multiple left-hand side, multiple attributes on the left-hand side, has the possibility of containing redundant attributes in the FD, but here we don't have. Okay, so right off the bat, you can notice that no redundant attributes. Okay, so this will never give us any multiple minimal covers because we don't have any redundant attributes. For the redundant FDs, we can then try to decompose this. We start with a slight rearrangement of this. So this is A. That one is copied. This is B. We can copy this. And then we remove one of this. Again, C, we can copy. F, we can copy. All right. What we can do here, we can look at the set of redundant attributes. Is there a way such that we can keep this? Can we remove the rest and not removing this? Okay. So first we check whether this is redundant or not. Okay. To check whether this is redundant or not, what we can do is we need. So this is our G. we need to check B plus with respect to G minus B to C. Okay, so basically, let me copy this. Remove this, compute B plus. Okay, from B you can go to A. From B you can go to A, you can always go to B. From A you can go to D and F. From F you can go to C. Okay? So at least we know that this is redundant. Now, the next thing that we can do is, once we know that this is redundant, we can try to move this. This is some little trick. We move this to the end. Which means now that when we want to check whether this is redundant, we have already removed all the redundant parts from here. Okay, so we do the steps again. We check whether this one is redundant. So A to D, B, C. From A you can go. So this one is redundant because from A you can go to F. From F you can go to D. Okay, so there's a possibility that this is redundant. From A to B, without this, you can get A to F to C to B. Okay, so this one can be redundant. This one is not. Yep, this one is not redundant. Okay, so keep on doing this. You keep on moving. You keep on moving the non-redundant part to the top. Move the redundant one in the middle, and then the one that you want to check whether it is finally redundant or not at the very end. Okay, so B to A is definitely not redundant. Okay, we move this to the top. C to A, C to B, B to A. Okay, so we can do transitivity from these two to check that this is actually not redundant. For this one, you have CA and then CB. Right? And then for this one, F to C, you have F to D, but D cannot go to anywhere. Yeah, D cannot go to anywhere, so this one is definitely not redundant. F to D, you have F to C, C to A, and A to D. So okay, so now this one is what we have in the middle. These three are definitely non-redundant. This one in the middle, we can try to mix and match, right? And then the bottom one is the one that we want to check whether it can be in the sum minimal cover or not. Right, so what we can do here, again, as after doing this, because we do not want to check whether this is redundant or not until the very last. Right. Until we have already removed everything that's redundant over here. Okay? So, at the worst case, what you can do is you can always have a backtracking method. We know that this one is redundant. So once we know that this one is redundant, is there anything else that is redundant? Okay, so A to B here now becomes, it's still redundant. Okay, so you can try removing this. Try removing this. C to A, C to B. Okay, so this one is redundant. C to B is not redundant. F to D is not redundant. So again, there is at least one minimal cover which admits this. Okay? So you can keep on doing this. C to D. C to D is not even here. But let's say you add this. C to D. Why can we add this? Because you have C to B, B to A, and A to D. So this one is implied. Given this, can we actually do the steps again such that in the end can we still keep this? Okay, so again, A to F, A to F. Without this, what we have is A to D, A to D. From D we can go to, okay, D we can go to A. Okay, so this one, C, D. Okay, so this one is not redundant. This one is still not redundant. This one is still not redundant. Okay, then we can try to remove one by one. This was redundant. I should not remove this one. Okay, so this one is redundant. Then A to B. Can we do away without this? F, FD, F, AF, FC, CB. Okay, so this one is redundant. Okay, try to remove this. C to B, B to A. Okay, so this one is redundant. C to B. C to D. From D we cannot go anywhere. F to D. Okay, so we try to compute C plus. D plus is nothing. Okay, so this one is F D. From F we can go to C. From C we can go to B. From B we can go to C. From C we can go to D. Okay, so this one, without this, A, F, C. So this one is redundant now. Oh, actually we haven't. So this one is still redundant. Okay, so we try not removing this, and then we move this to the bottom again. Okay, so it's basically just these steps. Okay, try to remove this. This one is again redundant. Then we do this. In fact, I believe you will see that this is actually completely redundant. Okay. In fact, typically anything that is not already written here will be completely redundant. Okay, which means that D to E is also going to be redundant. All right. So yeah, so that's basically the step. Try to put whatever you want at the bottom first. So if you try to remove anything that is redundant, that particular FD will be treated last. Okay? Do not try to remove that FD first. Try to remove that FD last, and then once you remove it, can you still, once you go into there, can you still remove it or not? Okay? So any questions on this? I can assure you that this kind of question will probably not coming out again. Especially in the context of final exam, because this is quite evil. In the sense that you have to kind of think about all the possible minimal covers. Okay, so question 6. Again, this one is straightforward. Super key. So if you want to find super key, we do not have an algorithm to find super key, but we do have a method to check whether something is a super key or not. Okay, so you can look at ABC plus, and then check whether ABC plus is equals to R. Okay, if it's equals to R, then ABC is a super key. A better way to do this is to look at this and notice that E is nowhere on the right hand side, which means that E must be part of any super key. Anything that does not contain E cannot be a super key. So these two are candidates for super key. A and B cannot be super key. So all we have to do is compute CDE plus. From C, we can go to AB. From A, we can go to D, E, and F. Okay, so CDE is a super key. DF plus. From F, we can go to. So we have DF. From F here, we can go to CD, so we can add C over here. And then from C, we can go to AB. Right, so this last two is a super key. Yes. That takes me back to your tutorial, the early part of your tutorial. You all remember this? Finding super keys. Finding possible super keys is exactly the same. You look at. Did I remove that? You need to kind of construct this. But again, if it's super key, then you have to look at everything, right? But basically, this is kind of inverted. So once you figure out that this one, let me open this in. Okay, so A is actually A, B, A, C, A, D. Okay, so so once you figure out that this one is a super key, then you can go down the chain, mark everything that is below it. It will be definitely super key. Okay, so you do again with B, B does not, C does not, D does not, and then you ignore everything here because they're already marked. Then you look at this, you look at this, you look at this, you look at this, and then you look at this. Okay? So it kind of can cut your search space by a lot. So these are all the super keys. And again, if you need to find all the key, then you just look at the minimal one. All right. The minimal one is given by this formula that says that this one is a super key. So let's say you look at this. If you want to check whether this is minimal, you look at this. This is a super key, and the subset of it should not be a super key. So this is a super key, this is a super key. So this one is false. This is not a key. If you look at this is a super key, and all the possible subset of it, which is this, is not a super key. So this is a key. Or you can use this method where you mark down everything underneath it to be non-key. Alright? Okay, but of course this one, there's a slight notion of a possible super key instead of an actual key. But when we talk about functional dependencies, it is very clear that we don't only talk about possibilities. Okay, so that's how you can find all super keys. Typically, I won't ask you what are all the super keys. Again, I will not ask you to type it down because the possibilities are a lot. Okay? Think about it this way. This is 4 attributes. All the super keys are basically almost half of the search space. Again, it's quite tiring to type all of this. A better answer will be find all the keys. Okay, because finding all the keys means that you either have to search through everything again and then just give me the minimal ones, or at the very least, I know that you know how to find a super key. Okay? So I will never ask find all super keys. Not in final exam anyway. Yeah. I kind of like the fill in the blank here, because fill in the blank I can easily mark also. And for fill in the blank, I forces you to a certain format. In essay, you can write anything, and that kind of tedious. However, if the question can be too hard, if the question is not just 1 mark, there might be some marks for marking. Okay, so I need to take care of that as well. Okay, so I'm toying with the idea of having fill in the blank where you can also fill in the working. Then if it's not exactly the correct answer, then I'll mark you on the working, right? But I need to look at the proper format for it. Otherwise, it would be just basically essay. Then I'll have to do manual marking, which is going to take longer, but it's possible. Okay. In particular, there will be either 1 or 2 SQL questions, and that will be essay. Right? The one that you definitely will not get is to draw your own ER diagram, because there's no way to input that image. CIT actually told me that they have some kind of feature to allow the camera to work, but then that's also not going to be useful. Basically, because you're using your computer, not all laptops have camera, and even then you need to bring your laptop up to take photos. Okay, so no, I'm not going to do that. Right, so for this one, because this is MCQ or MRQ. In the case of MRQ, there is another way you can check whether things are key, and it might be simpler, especially because all of these are 2 attributes. So you can always compute AB plus. Okay. And again, as we know, if you do not have E, you cannot be a super key. So it's either DE plus or EF plus. So we end up with these 2 again. DE plus, nothing. EF plus is also just EF. The correct answer is not to choose anything. Yeah, I was toying with the idea that I don't need to put this, because this one is taking up 1 choice, and also it kind of gives you the it may give you the hint that there might be none of those. But here, you may not know whether there's none of the above. Okay, but this particular one, so the correct answer is not to fill in anything. Right? I quite regretted it, because a lot of students actually say that they get the warning. Right? If you don't fill in anything, you get the warning when you try to submit. Okay? And then you just have to have faith in your own calculation that it is correct not to fill in anything. Oh wait, actually EF is a key. Huh. I missed this. I keep on looking at C. Yes. If you can get C, you can get almost the rest, except for E. So this one is actually the key. Then those students who actually skip this didn't actually do it properly. Because I remember there was some student who complained about this. Okay, so the next thing is, how do we know that this is, we know that this is a candidate, we know that this is a super key. From here we know that this is a super key. We do not know yet whether this is a key. So what you need to do is you need to find E plus, which is just E. You need to find F plus, which is just F, A, B, C, D, F. Okay, you're missing E. So, in the general case, especially because these are typically two attributes only, you compute the attribute closure of this, and then you compute the attribute closure of any of the subsets. This one has 6 attributes. So even with 6 attributes, typically on complex enough functional dependencies, the keys are typically small. If the key is large, it's usually not a good relations, because it means that it is not entirely a single object. You can decompose it either to BCNF or 3NF. Okay? So all the prime attributes here is basically, if you say that this one is a key, then it's just ENF. If this is the only key. Okay, but CF is actually also a key. CE. CE is also a key, because if you can go to C, you can go to everywhere else. Okay, so CE is A, B, C, D, E, F. BE plus is also A, B, C, D, E, F. AE is also A, B, C, D, E, F. Okay, so A here, from A you can go to D, you can go to BF. From B you can go to C. Okay, and then from C you can go to A, but we know A you can already go to the rest. So this you can go to A, B, C, D, E, F. B also can go to A, so again, this one, everything can go. The only exception is F. F is not anywhere. Okay? And the reason why we know is because now we have 4 candidate keys. AE, BE, CE, and PE. EF. Sorry. So D is not. D is not a candidate key. Right? If you have this, and you must have E. Okay, so we have 2 conditions here. These are all the current known key. We have 2 conditions. One, all super key must have E, and all key cannot contain the known key above. Okay? Now you try to find all 3 attributes. All 3 attributes that include E will be E and D, and then everything else is already covered from here. Right? If you add A, okay, so you have DE. If you add A, this is a subset of this. If you add B, it's a subset of DE. If you add C, it's a subset of CE. If you add F, it's a subset of EF. Okay, so AE, BE, CE, and EF are the only keys. So you get A, B, C, E, F without D. Okay, any questions on this? Question 9. You're given this, and then you're given this decomposition. You are asked whether this is BCNF and whether this is lossless joint. Now, there's only 2 fragments over here, so checking whether it's a lossless joint is kind of trivial. Okay, you look at the intersection of this, you have A. And then you compute A plus. When you compute A plus, based on the previous calculation, you get A, B, C, D, F. Right? So at least you know it's lossless. And then whether it is in BCNF or not, we need to check this one. R1 is definitely in BCNF. So we need to check R2. Okay? So to check R2, we just have to find a counterexample. Remember from before, we know that all of this is prime attributes, and then you look at the prime attribute minus the attributes that are not present in R2. Okay, so basically A, B, C, F. The reason why we get this was because E was not on the right hand side in the first place, which means that A, B, C, and F must go to everything else except E. Okay, so if you compute A plus, this one must be A, B, C, D, F, B, C, and F. Okay, so all of this have as the right hand side a primary key or a key, a super key. Okay, so yeah, this is in BCNF. Right? We can actually check this. I keep on forgetting that we do have this one. Just need to change this to this. A, B, C, D, F. BCNF violation check. Yeah, I need this. Ah, yes. I think there is another column. No, it's not. Let me try to simplify this. Let me check with the simpler one first. So it works. So it's not that. It must be comma. Oh wait, that's not good. Ah. This one I didn't get an answer, so don't know with this. A, B, C, D, F. I should have print some error message. Okay, in any case, there should not be any violation here. And then this one, you can first check whether it's whether this decomposition is dependency preserving. Why doesn't it work? Okay, I've given up. We can check whether this is dependency preserving or not by looking at. You can first check whether it's dependency preserving or not. Okay, if you know that this is dependency preserving, then you can just check whether this is in F plus. Okay, so A to D is definitely in F plus because of this. CF to D, you have F to D over here, so CF to D is in F plus, right? So note that all of this, okay, so this is something simple in this particular question, because all of these functional dependencies are in R2. None of the functional dependencies actually belong to R1. Okay? So it means that whatever is true in original R is also true in here. Because at the very least, this will be parts of the projection on R2. So yeah, so this one is definitely preserved. These two are definitely preserved. For the fourth one, AB to D, whether it's in FR2, you just have to check whether it's in F plus first. Okay? So AB, again we have A plus as this, so definitely AB to D is in F plus. It is definitely going to be in FR2. Alright, so this one is actually A and D. Let me try last one. Let me write it down on my own. Okay? I think the problem is this, there's a duplicate. Then you can do this one, BCNF violation check, it is in BCNF. Alright? So in fact, if you want to do this, do a BCNF decomposition, you get back exactly this with all the steps. And it is dependency preserving. Okay? If you look at the 3NF decomposition, you get something that is very, very small. Okay? So any questions on this? Question 10. This is a simplified form of your assignment 4. Simplified because, as you can see, what you need to write here is pretty much simple. And this is actually MCQ or MRQ. The step for this particular one, the easiest way is to copy this one first. So this is our set of function dependencies. We copy this one, we try to solve for this. Okay, so fill in the blank. Decomposition of 3. There are a lot of ways this can be decomposed. In particular, it can be EF to E, EF to C, EF to D. Okay, so currently we are not exactly sure which one it is. For this one, it is quite clear. We can only look at the top two. The one that has CD is 1. So this must be augmentation 1 with E. Right? So this one is also augmentation. Actually not yet. Not yet augmentation. Because we need to know what this is. We need to know where this one is used. Okay? This one is used with 4 and 2. Okay, so 4 here must be combined with 2, and 2 we know that the domain of this is C. So we know that for this to be correct, the other side must be C. Okay, so now we have filled this in, and now this one makes sense. So EF to C and then C to AB, and then get EF to AB. Right? So our final objective is this. A, B, C, D, E, F is a union of a few things. Right? So the union will be 3, 4, 5. Now, whether or not 6 is part of the union, we need to figure out whether there is anything that is missing. What is missing is basically F. You have A, B, C, D, E. You're missing F. So 6, at the very least, 6 must have F. Right? Because 6 must have F. This can be EF to F, in which case this is reflexivity. Or you can also augment this with F, with EF. So there's a few possibilities. Augmentation of 1 with EF. Okay? You can think of a lot of other things. What matters is that for this particular FD, the right hand side must contain F, such that the union of all this contains all the attributes. Okay, so we can then start filling this in. For question 10, this must be, because it's decomposition of 3, this one must be EF to C. Alright? You cannot put EF to D, because if you put EF to D here, the rest doesn't work. The only reason why this one works is because of the transitivity. If you put D, the transitivity doesn't work. Alright? And if you put with E, then the transitivity doesn't work as well. Okay, so the only possibility for this is EF to C. Question 11. Question 11 is this. We have two possibilities. One is augmentation with E. The choices are missing. Yeah, basically it must be augmentation of 1 with E. Right? Wait. Yes. It can only be augmentation of 1 with E. Right? You cannot put with EF, because if you put with EF, then you have ECDF over here. Right? So it doesn't work. For the second one, it is either reflexivity, augmentation of 1 with EF. This one also works. Basically, any choices that give you F on the right hand side can work over here. Okay? The right hand side must contain F, the left hand side must be EF. So anything with that property can be used over here. And then question 12, this one is basically just 3, 4, 5, 6. Right? So yeah, this has multiple possibilities, so it kind of forces you to look at the rest of the possibilities. Okay, so now for this one this is the part where it's actually essay. So I was toying with this idea of asking you to write an essay that is basically giving you, you need to write one possible minimal cover in this particular form. Right? So I do have a solver for this. I can simply check. So the way to check whether, if I'm giving you a G, right? You already know F. So let's say we are in the MRQ kind of setting. If I'm giving you a particular G1, and then I'm asking you whether is G1 a minimal cover of F. Okay? So there's a simple trick to do this. One is that you need to check the F is equivalent to G1. Or let's just put it as any kind of G. This is the first condition. How do you check this? Well, for any A, for all A subset of R, you must have A plus with respect to f is equals to a plus with respect to g. Okay, and it must be true for all possible a. And 2, if you apply algorithm number 2 on g, you will get back exactly g. Right? That's the second condition. Why? Because we know that algorithm 2 basically removes redundancies. If the set of functional dependencies that you give me is not minimal, it will not be equivalent. Okay? If it's equivalent, then I know that g is minimal and g is equivalent to f. G contains no redundancies. Okay? So this is checking. Checking is straightforward. So for any, if there's an MCQ and I'm asking you whether this is a minimal cover, you can just do this two. Of course, this one is quite difficult to do by hand. So yeah, you need to be careful. For this particular one though, so what you have to do is you have to find one possible minimal cover. So again, I think we already did this, which was here. So I look at this. This can give me at least one minimal cover. So I need to check whether this is redundant, this one was redundant, this one was still redundant. Which is it redundant now? AFFC CB. Okay, so yeah, it's redundant. C to A, you have C to B, B to A. Okay, so this one is redundant. C to B cannot be redundant. F to D, FC, CB, BA, so it's not redundant. B to C, oh, this one is actually redundant. Okay, one possible minimal cover. Okay, so done. Okay, you can give me anything as long as it's a minimal cover, it's fine. Question 13. This is kind of you have to give me a lossless join dependency preserving tree and F decomposition. Okay, so again, you can use the minimal cover that you compute here, and then you just form. R1 is A, F. R2 is BA, or AB. R3 is CDF. R4 is BC. Okay, and then you figure out one of the key. We have already computed the keys. Okay, and then you just choose one of these to be the additional ones. Notice that none of this is redundant. AE is not contained here, BE is not contained here, CE is not contained here, EF is not contained here. So you can add any one of this. Let's say BE, and then you're done. Alright? Now again, you can always give anything else. Okay, because here I don't really care whether you use algorithm 7 or any other algorithm. What I want you to give me is a lossless join dependency preserving tree and F decomposition. Okay, so in fact, the way I mark this is I just check for all these three properties plus one more. So marking is typically done using whether it's a valid decomposition, whether it's a lossless join, whether it's preserving, dependency preserving, and whether it's in tree and F. Okay, these are the only thing I want to check. Okay, so to check for validity, what I need to check is whether or not all the attributes are present. If there are missing attributes, let's say you forget this, then you do not have this property. Okay? So this one, check all attributes are present. Lossless, this one is just figure out whether there's any decomposition that make it lossless. So you can apply theorem 1 again and again for all the possible combinations of this, and then one of them is whether or not one of them is going to be lossless. Okay, I need to draw here. So for exam question, I won't ask you anything more than 4, basically. Checking lossless join on anything beyond 4 is very, very hard. Okay, so remember that for 3 fragments, we have this particular, okay, so for 2 elements, for 2 fragments, we have this particular tree, and then we can apply theorem 1. Right? So this is trivial. You only have one possibility for this. If you have 3 fragments, you need to check whether this is lossless join. You need to use a combination of theorem 1 and theorem 2. Okay? If you want to look at everything. The property of this is that the leaf, you have 3 leaves. Okay? For any n fragments, you must construct all possible binary tree with n leaves. Okay? So let me illustrate what happens if you have 4 leaves. If you have 4 leaves, you have this. And then you need to check all the possible permutation of this with this shape. And secondly, you have this shape. And then you need to check all the possible permutation of this. Okay? Luckily for us, this one is isomorphic to this. Okay, this is isomorphic by rotation of these two. Okay, but again, this one is also 4. Okay. Now imagine for 5, you have a lot more possibilities. And then you have to check for all of them. So, yeah, so if you want to enumerate everything, then it will be a lot of work. What you can do is you can look up online. There's this algorithm to check for that. It's called the Chase algorithm. Okay, we're not going to discuss that because I won't ask you anything more than 3. Okay, 3 is possibly the maximum I will ask, or at the worst case 4. But 4, I don't think I will ask that in final exam anyway. Okay, but for any larger number, using combination of theorem 1 and theorem 2 is not going to be feasible. It's not going to be computationally feasible. Okay, so you need a different kind of algorithm. And there is one algorithm called the Chase algorithm. Okay, so that's basically what I'm checking. For dependency preserving, we have algo 4. For 3NF, we have a modified algo 5, where I add one more condition, which is that from A, so the step of algorithm 5 is that given any A, I compute A to A plus, and then X is equals to A plus intersect Ri, and then I need to check A less than X less than Ri. Okay, so this is the part on BCNF. One more step is that X is a subset of prime attributes. Okay, so the modified algorithm 5 can be used to check whether you satisfy the 3NF property or not. Right, so you just need to check whether X is a subset of the prime attributes. And this is the prime attributes of Ri with respect to Fri. We do have an algorithm to check for prime attribute. Before, you just have to compute all the keys, and from all the keys you union them, and that's your prime attributes. this can be pre-computed at the start. You say it's P is equals to this. Right? So yeah. So if it does not satisfy these three conditions, then it's not in 3NF. Alright, any questions? Yes. Possible. Like in assignment 4, there are a few subtleties, right? So one is that whether I ask you to use algorithm 6 or not. If I ask you to use algorithm 6, then you have to enumerate everything. But typically, you can check whether there can exist one or not. You can check whether there can exist one or not by just trying to compute one minimal cover, and that is guaranteed to be 3NF, and then you check whether it's actually BCNF. Highly unlikely. Okay, because the minimal cover contains no redundancies, and if the one without redundancies forces you into 3NF, it is highly unlikely that you will get into BCNF, right? So yeah, 3NF is kind of the key. And also the other thing is that the reason why we cannot have BCNF is because of the this is not a good attribute. This is not a good example. But typically, when you have all functional dependencies, all attributes appear in any functional dependencies, yet you still have shared key, you have an overlapping key, then typically you can never get the BCNF. This is a bad example because in this particular case, E does not appear anywhere. So even if you add key, if you add E, it will satisfy BCNF trivially, right? So for this particular one, E is totally redundant. Even though there's an overlapping key, E here is totally redundant in the sense that E should not belong to A, B, C, D, F. Okay, but if E should belong to A, B, C, D, F, and you have an overlapping key, you cannot get a BCNF. Okay, so that means E must appear somewhere here. E appears somewhere, but so E must appear somewhere, and E is, so it's kind of, E is redundant but not totally redundant. And in that sense, you cannot get it to be BCNF. Okay? So that's another check to see whether BCNF is actually possible. Or to do it another way, you can actually get BCNF, but if you get BCNF from an overlapping key, it can never be dependency preserving. Right? In particular, that dependencies that require that shared key is not going to be preserved. Okay? So yeah, so that's basically how you check. So any questions? Yes. For that, you need to look at the fragments that is generated from that. No. I don't have the question, but you look at you look at the decomposition, you look at the relations that is given by that. Okay, so you have a few things. So relations, if there is a primary key, relations is basically equivalent to table. So look at all the tables generated, and for that particular table, check whether it is the correct table or not first, and then for that particular table, that will become one of your decomposed fragments. Yeah, because so what happens is that it basically means that if you use the particular ER diagram, given your original constraint, you will not get lossless join. Okay, so that was the meaning of the question. And again, this is basically your tutorial 3. Actually, not exactly a tutorial 3, but if you remember this, I mentioned that which one of this is correct is we do not know. Okay? The reason why we do not know which one is correct is because we do not know what is the constraint expected from here. Now, if you look at this, and only this, if you look at, basically you look at design A and only design A, and you look at all the functional dependencies that is generated by this, you will find that this is actually lossless join and dependency preserving. Okay, it's always the case because that's how we get ER diagram in the first place. But if you look at the functional dependencies for this, and you use these fragments, so you get the professor's table with PID and PName. You have the teacher's table with PID, CID, year, and SEMNAM. You have the course table with CID and CNAME. But this particular functional dependencies, then you will not, you basically either don't get lossless join or dependency preserving. Actually, I haven't checked for this. But for this one, you definitely, if you use this, you will not get lossless join. And we already have a simple example for that because you can never know which supplier sells which part to which project. Okay? This particular design is correct. It is correct in a sense that we do not, if we do not know what the constraint is, it is correct, trivially correct, right? And it is trivially correct, but the reason why this is correct is because we can never know this information. This information is always unknown to us is if we use this design. If you want to know this information, then this design is wrong. Right? So if you want, but this design may not be fully correct as well because in this particular design, you do not have, you cannot, you do not know whether this supplier can supply this particular part. Okay, you need to well actually actually it's basically this. When the supplier sells a particular part, okay, so when the supplier sells a particular part, it must be attached to a project. Okay, so you cannot know all the parts that can be supplied by a supplier unless the supplier has already involved in a project in the first place. All right? Okay, so there's a subtle differences there, and the subtle differences, basically, if you need this, if you have this particular constraint, if this is the constraint that you need and you use this, I believe what happens is that it will not be in BCNF. Okay? So yeah. So for that particular question 10 to 12, you will see that in one of them, in only one of the answers, you will get all three properties. And that's basically the ER diagram that we want. Okay, I think it's C, either B or C, I forgot which one. But if you have one of those, you basically get lossless join, dependency preserving, BCNF decomposition. So that's how you can try to design your database if you do not know anything about ER diagram. Okay? And then you will arrive at a kind of an ER diagram format, assuming that your functional dependencies can accommodate BCNF. Otherwise, you may get stuck with 3NF. All right? Okay, so any other questions? Yeah, so assignment 4 is already marked. I will upload it tonight. Yeah, but basically question 8 is one of the lowest scoring one. The augmentation must involve multiple. Huh? This one? It works. I forget what's the... Did you follow this format? Because many of you put augmentation off and transitivity off. So if you use off here, I haven't really write a proper parser for this, so it's just a simple string parsing. But yeah, so if you put off, then the entire check will not go through. Yeah, I don't have question 4 with, I don't have assignment 4 with me. Oh, correct. Yes. Assignment, right? Okay, so let's see question 8. Is it AB to D, A to BC, B to C, DE to D. And the relation is ABCDE. You need the relations because if you use reflexivity, you need this. The target is AE to ABCDE. Okay? The first one is this. And this is given. Right? The second one, either you want to continue from here or you want to continue from given. But you can get, we want to get AE. Okay? So to get AE, you need to augment with E. But if you just augment with E, you get this. Basically not enough. So you need to augment as much as you can. Now the second one is either this or this. The only thing that we are missing is D. As long as we can get D back, then we are done. Alright? As long as you can get something involving A, B, C, D, E. And on the left side we have, so what I want eventually is this. ABCE to ABCDE, because here you have AE to ABCDE. This one is transitivity 2 and 4. Okay? So in the intermediate one, I can always, oh sorry. This is here. So in here, I want to do augmentation of 3 with ABCE. And this will give me a lot of choice. Because ABCE, if I add with D, there, I get ABCDE, and this one is I still get ABCE. This one I also get ABCE with ABD. So again, so I can choose any one. So if you check, it's correct. All right. And again, if you use BE to D, it is still also correct. All right. So any questions? It's in the tutorial room. All right. So try to rehearse. You don't have to show all the functionalities, just show us the interesting functionalities. Because there's only like 15 minutes, right? Try to keep it at around 10 minutes so we have 5 minutes for Q&A. Yes. Which one? This one? Yes. But it's a set. The definition is that it's a set, right? The set does not contain duplicates. This one is equivalent to this, because let me, in the lecture, our first lecture on function dependency is on 8, right? The terminology that we use here, set of attributes. So they are equivalent. Right? And then we use lowercase to denote subsets of attributes in R. Okay? So this one is denoting you're creating a set, and the set should not contain. If there's any duplicates, you remove them. Okay? And they are equivalent. Okay? So yeah, and truthfully, at the start, I wanted to give you a false hope that you can use extended Armstrong axiom, but truthfully, it will not help. Because of the way extended Armstrong axiom is formulated, where even when you want to use the union, the left-hand side must be exactly the same. Okay, so it will not help you much. In fact, I tried my best to use with union, and then it doesn't actually give me anything shorter than 5. And I thought giving you false hope of allowing you to use union is actually pretty evil. So that's why I decided not to force you not to use extended Armstrong axiom, because otherwise you will go into a search which basically is useless. Right? So yeah. Any questions? Okay, so okay, we can try to go through some of this. BCNF. Yes. I can show you the steps, because this one, when you put the BCNF decomposition here, it doesn't actually generate all the possibilities. This one is actually 6 out of 72, I think. If you, yeah, question 7, right? If you use algorithm 6, you try to permutate all the possibilities that can be generated by algorithm 6. 6 out of 72 is actually dependency preserving. Okay? But again, the general idea is that you try to look for the 3NF decomposition first, and then check whether it's BCNF, and then from there figure out whether this can be done using algorithm 6. So yeah, any question? Yeah, this one is aggregates. So it's basically just saying that this borrow table should have this 2 as the primary key and this 2 as well. Okay, so the primary key is 4. So you need to include 1, 2, 3, 4 within the borrow. Sorry, 1, 2, 3, and all this. So it decomposes into fragments containing LID, BID, INAME, and this. Right? Okay, so if there's no questions, then so I'm going off to Japan on Wednesday. So unfortunately, there's no consultation this week. But I'll try to book a room for the reading week, and then we'll see if we can have. It's very hard to book a room lately, so I'll have an announcement. Try to have 1 or 2 consultation sessions during the reading week. Okay. If you need, if I cannot find and you need a personal consultation, just email me. Or if my door is open, then just feel free to come in. Okay. Otherwise, what we can do is we can have a group consultation where I'll put up a doodle again, and then you can register there at the doodle. But please do come for that. Okay. So, all right. Thanks for coming.